Hi, I'm Alfonso Guerra, founder of Apocalypse Software. We do productivity tools, but this is the West Coast Machine Learning Group, and we're discussing a paper, um, Less is More, Recursive Reasoning with Tiny Networks by Alexia Jolicoeur-Martineau. Sorry for butchering her name. Um, and it focused on a new technique for um, reasoning for machine learning. It is based off of another one called hierarchical reasoning model, which, as it says in the abstract, uses two small networks. Uh, and I'll just read part of the abstract, recursing at different frequencies, um, so that instead of creating a large uh, uh, network, memory intensive network that has been that takes a lot of time to generate. It uh, creates a very small model, and what it does is, as it uh, instead of using the a large network to uh, provide reasoning, something that has been pre-computed, it will on the fly sort of generate the answers that it needs by repeatedly recursing into the network and refining its reasoning as it goes along. Um, so what this paper presents is a derivative of that called the tiny recursive model, which goes even further along that line because they believe that there are some optimizations that can be done off of the hierarchical model, we'll call HRM. And in the paper, they call theirs the tiny recursive model, or TRM. Um, so with that, they're claiming that a simpler recursive reasoning approach uh, does even better than the HRM with a tiny network with two layers and 7 million parameters. Um, and they claim a better accuracy on several of the benchmarks that are typically used for large language models and other um, machine learning models. So as they go, they first talk about the certain drawbacks that LLMs have when they're answering certain types of questions, and so they incorporate um, other techniques such as uh, chain of thoughts and test time compute, and so they describe how these processes work and um, other things that must be done on top of the LLM um, architecture in order to get better results for the benchmarks. Um, and so they bring up uh, the model that was proposed in another paper through their HRM, which yielded better results on a smaller model because it depended on two primary techniques which they added. One was recursive hierarchical reasoning, which basically iterates through these models repeatedly, and it uses certain hyperparameters to allow the operator to specify what their work would be, um, or how it should operate. And they in their paper they present two uh, notations, um, FL for the high frequency and FH for the low, um, to determine how to iterate through these networks, and that each network uh, generates two outputs, uh, ZH, the high frequency one, and ZL, the low frequency, and those are then used as inputs to the network again. So the authors of the HRM paper uh, present that their model was based on reasoning, based on how biological models process information. So they're basically trying to um, build their technology on top of uh, an architectural, a biological model. Um, and so the other technology that the HRM paper presents is a deep supervision, um, in which and this I'm a little fuzzy on. They the outputs that are generated through these steps, uh, recursing down the layer, recursively iterating through the model. Um, it basically reviews their work and does some corrections or guidance calculations to yield a better results. And these two um, features on top of their tiny models uh, got better results. And uh, in this paper, they talk about how another uh, analysis from a separate group analyzed the HRM and determined that the deep supervision was um, the main way that it was able to that the HRM was able to improve its results vis-a-vis the LLMs. And they talk about how the the accuracy for one uh, benchmark went from 19 to 39% accuracy. And the other technology presented in that paper, the recursive hierarchical reasoning, was only slightly better. Um, they because they tested them independently. Um, so, but in this paper, they determined that um, the recursive reasoning could be improved substantially with some other techniques, and so they present the tiny recursive model with an even smaller models or network than the HRM paper does. Um, and let me scroll forward here just so that we see this was the pseudocode for the HRM model, and um, begins here in the training, and it determines the number of. Uh, this is the part that does the deep supervision, um, and here's where it calls the recursive reasoning uh, here. But this supervision is where it determines where the loss is, and um, processing for that, they're able to get the results on the next iteration to be improved. So let me stop highlighting this one here. So the uh, in this paper, they're talking about at this point is where they can do yield better performance. That this one is already significantly better than typical LLM work, and that improvements here would be even better. And they claim that where is it? Yeah, they claim that they were able to improve the performance on the Sudoku Extreme from 55% to 87% accuracy over the HRM, which was already better than LLMs. The same with Maze Hard and the other benchmarks that are used here.
Yeah, Alfonso.
So, yes.
Yeah, quick question. Just did you dive into the deep supervision? What exactly that is saying. I'm not sure I have a correct understanding of it.
Yeah, that's the part that I wasn't too clear. Um, here's the code,
Mhm.
pseudocode for it, and they're getting the data from the recursive um, coding of the network to extract an answer, and um, then they are um, they're determining, I guess, the loss of what uh, how far off the answer is from what's optimal, and then they uh, generate. When is that complete? They generate a a step to improve it for the next iteration, um, to optimize uh, the direction that the network is going, and then or that the model is generating, and then that's used for the next step through the network. So let me see. Well, that this is from the deep supervision from the original HRM model,
Right,
and
right.
in this paper, they're not specifically addressing how that works. They're focusing on the work of the recursive um,
Okay, okay.
reasoning. But in this one, in the original paper, um, I didn't I didn't take a look at the original paper, but it seems that this is navigating um, the uh, the results generated through each iteration
So some,
through the network to kind of guide it towards where the correct uh, answer would be.
okay.
So it,
So go,
if you guys want, I can try and shed a little bit of light on this.
Yes,
yeah,
please.
feel free, please.
Um, so I think what we want to do is we want to disentangle two different aspects of this. So one, this is a recursive transformer formulation. This is not the first recursive model, okay? So a really, really super simple recursive transformer would be you say, hey, I have this GPT-2 model and it has 24 layers. I'm going to replace it with a model that has only one layer, but I'm going to repeat it 24 times. And if you do that, you can get something like 90% the performance of GPT-2 at 1/24th the amount of storage of weights. So you can't get the same performance, but I was even surprised. I don't really have a mental model how you can even get like 90%. Okay. So the hierarchical recursive stuff that's in that top part has two for loops basically, and um, and it just has to do with how it repeats its layers in what order it's repeating them. Okay. So if we just set that aside for a second, then the deep supervision just means we're going to run our model 16 times or whatever. Okay. Um, during during training, we're actually updating the weights each of those 16 times. So it's a little bit just like running 16 epochs, sort of, right? Except the huge difference is when you're just training any old model, like, the old CNNs, AlexNet or whatever, each time you start an epoch, you're starting from scratch. In this case, there's there's hidden state in there, and what they do is they run the 16 in a row on the same data, and they keep the state in between each of those runs. So that's why they don't just call it supervised learning. Okay, that's why it's got this deep supervision name, because if they were just resetting the state every time, it would be identical to regular old supervised learning. But in this case, it is different, and so it does kind of require a different name. Okay.
So is it,
So,
am I understanding correctly? Then it's kind of, if the number of iterations is 16, that it's kind of back propagating through those 16 layers.
but they don't do that as a way of speeding up and simplifying the process. So they do one of the 16 and they do backprop on just that one run. And then they do the second of the 16 and then they do backprop on just that one, not the first two, but just the one all by itself. And then they do the
And
third
that,
one and they do backprop. So it's 16 separate runs, as it were, right? In terms of the gradients are only dependent on that one of the 16. However, the starting point is not identical for all 16 of them. The starting point is using data from the endpoint of the previous of the 16.
Is,
gotcha.
is it fair to say that each of the, except for the first one, each of the successive ones are attempting to run based on the error? They're correcting for the error, or they are correcting for the original data, or they're still running from the original data?
Yeah. So they are not correcting the error in the literal sense, the way that gradient boosting, you actually subtract your prediction from the correct answer, and then you say, I'm going to predict on that error. Okay. Rather, the mental model I think that most people agree on is they're refining the answer from the previous step. So you know, if you're solving Sudoku, in the previous answer, you had a bunch of one, twos, threes, nines, and then you say, now you're allowed to change some of the numbers. Do you want to change some of the numbers to try and make the answer even better? You know, um, does that answer your question?
Yeah, yeah.
Makes
Yeah.
sense.
So
Hey,
I'm trying to think of a model. So if you guys remember StyleGAN, there's other models, but StyleGAN is a model that had a certain input that was just this constant input, um, that all the images it generated started with this square set of numbers, and then as it went through the layers, the the input information would condition uh, that. And ultimately, with the knobs that you would do on StyleGAN, you would get the face, male, female, older, younger, color, hair, all that stuff based on the knobs you set. But the input was a constant. When you're training StyleGAN, that input was learned, but basically you're starting from scratch every time you do a training instance. Imagine what if instead of starting from scratch, you somehow were able to start with the the tentative answer from the previous run and you inserted that at the beginning of the pipeline instead of just starting with a noise vector. Um, and and so in this way, it's iteratively refining the answer, and it's just a very very different way of calculating than a traditional CNN, a traditional transformer, pretty much a traditional anything.
Ted, do you have any intuition why? So what the mental model I'm seeing then is it's kind of like we're training one layer at a time going up by preconditioning it on the output of the kind of the previous layer. Um, do you have any intuition why that is better, or why they selected that rather than just training the whole stack and just back propagating it through the multiple layers at once? Does that make sense what I'm
Um,
saying?
yeah, I think Alfonso will get to in the paper. There's some changes they made from HRM to TRM, and they actually include more back propagation. But it would be if you have an 18 layer model. I don't know what the exact math is, but an 18 layer model, and you repeat it 16 times. I don't know what is 16 times 18, but it's like almost 400. Okay. And so if you have 380 something effective layers, then back propagating through all
Yeah.
300 of them would be kind of expensive from a memory perspective, and it would be a little bit slow. But I do believe the question you're asking, yes, it would work. If instead of doing deep supervision one at a time, they just did all 16 at once, they the model might actually train slightly faster, but at a like 16-fold increase in GPU memory needed to train the sucker.
Gotcha.
And so they
Gotcha.
were able to do these experiments, I think, just on like a consumer GPU. So
And um, would you say that for this architecture that these models are better for um, processing on the edge where um, it because it doesn't have the memory requirement, it's basically uh, building up the network as it goes along, or computing the network as it goes along, which it is only temporary, but it's able to do that. Um, I don't know if it would be faster, but certainly using a smaller network than the regular LLMs would need. So that this is basically for mobile devices and other devices at the edge.
yeah, I think most of the research in recursive tr transformer architectures is thinking about smaller devices. Uh, but again, we do need to be careful that I gave this is more complicated, but a super simple thing would just be you have one layer and you repeat it 24 times. Okay.
Yeah.
It's a lot smaller memory wise, but again, it is still just as much compute as your model that has 24 layers. It just needs less memory because you're repeating the same one 24 times, but it's going to be just as slow compute wise as that. So it's not quite the silver bullet when it comes to smaller devices. Because if you said, "Oh wow, I figured out a way to take GPT-5, which is we don't know, but it's ginormous, right?" And if you said, "I can just repeat 3 layers 1,000 times and I can get the same performance as GPT-5," that would still be an amazing result, but you still couldn't run that on your phone in the sense that it will fit on your phone, but it'll output like one token every 5 seconds because you have to run those 3 layers 1,000 times to get one token, and then you have to run those 3 layers 1,000 times each to get one token. So it solves part of the problem, but it's not the silver bullet.
So it's in some respects more like compiled versus interpreted code, or Python versus C++, in that uh, with these recursive models, they're having to figure it out every time along the way uh, on edge devices, on mobile devices, versus LLMs, which have it pre-computed to a large extent, and it's just uh, building the answer from that.
Yeah, like if I told you, "Hey Alfonso, I wrote a program and I can compute all the factorials up to 10 factorial, but I just hand wrote out a bunch of multiplies." Right? And you're like, dude, I can write a for loop and it'll only be 3 lines of code and it'll do the same thing yours does. We would say that your program is definitely easier to understand, more efficient, whatever. But at the same time, it won't necessarily run any faster than my ugly
Mhm.
thing that just does all the multiplies handwritten out.
But is that going to be at the time that you're creating the inferences from it, or is it uh, is there the difference of the computation, or the difference of the generating the tokens uh, going to be when they're actually querying uh, the models?
Yeah, so that's my point is that if you again, this is a little bit more complicated, but if you have one layer you repeat 24 times, it basically takes the same amount of time to train it as a 24 layer model, and it takes the same amount of time to spit out a token as a 24 layer model. It's just 24 identical layers instead of 24 unique layers, but the effective amount of matrix multiplies you need to do is just the same.
Okay.
So, and again, I'm not trying to be overly dismissive. I love that there's research on something that's different. But I think, yeah, just understanding that recursive The the one really big trick that people use with recursive, and they do talk about in the HRM paper, and they talk about in this paper, is if you repeat this one thing 24 times, there's the possibility you realize, hey, I actually have a pretty good answer and I don't need to repeat it anymore. And so you can stop early. So you can say, I'll stop after 4, I'll stop after 10. I won't have to do all 24. That's one of the big potential wins. Other than that, though, it really is just, um, in my opinion, it's not really going to solve your edge device phone problem because it's still, going to be just as slow.
Well, it's all one part of it, the footprint part of it.
Yeah.
Yeah. So in that respect, you can have several different models that that you have on a phone, which are application specific, rather than having one general purpose one that tries to solve everything.
Yeah. Small is good. I mean, there's definitely a benefit of small. Um,
Okay.
Okay.
Well, and this is their flow chart for the architecture and how they do it. And as Ted was saying, it keeps local variables of the state um, as it's processing, and each uh, iteration through the networks for the results where I guess it's fine tuning its answer to come up with the correct um, solution here. Um, but here's their again the original paper, or the paper for HRM. The the ideas behind it, and why they or the way that they recurse through the two frequencies, which had its origin in their biological model. Um, and so, as he said, it's they start from the initial state. They have the original state. They start with initialized embeddings from the network, and then through each iteration, each recursive step, they will take the results from the deep supervision step, and um, where is it? And then applying it to the recursive reasoning model, uh, which I already went over that code. Um, so they talk about the results from the original paper, and some of the ways that they saw that they could um, uh, optimize that, or what the potential avenues that they could go in instead. And um, I guess this is where it's doing the examination between the steps to yield I guess the loss on it, and how it's going to redirect the parameters it's going to get for the next iteration. There's the Okay, so they're using gradient approximations instead of back propagation through time uh, in HRM. And so they basically gave the overview of how HRM did its job and how it worked. So then they looked at that and they said, again, what they were going to address in their tiny recursion model. Okay. Um, so they talk about some of the uh, decisions that HRM paper took. They only back propagate through the last two uh, recursions in their model. And as Ted said, when they found that they were basically at a decent point in their answer, they can stop processing and generate the tokens. Um, and this paper's exactly.
Is anybody familiar with that implicit function theorem? Kind of what that means, how that works?
I don't know the theorem well, but the idea is um, is in a recursive neural network. Okay, um, what people are are thinking is happening is that the model is slowly converging on an answer. So it's a little bit like what do you call those in differential equations, like attractors or whatever, where you have a fixed point where um, where once you go there, then you just don't leave, you just stay there. Okay. Um, and so so the idea is that if you build something, these they wanted to make them really fast. They actually didn't repeat that many times. Okay. So if you see two, three, six, relatively small numbers. But in other cases where people have tested recursive models, maybe they'll repeat them 10 times, 20 times. Okay. At that point, the difference between 20 times and 100 times, it's still in the general genre of a lot. And so if you had some computation that wasn't converging to a fixed point, if you were just like adding 2 every time, then the difference between 20 and 10 and the difference between 20 and 30 would be huge. And so they say like these things can only work if they're sort of slowly converging to a fixed point. And that's this, I don't know the exact theorem, but that's the idea here. So the idea is that if you if you give it an I can't think of a great answer, but like if you wrote a little program that's like approximating the value of pi, and you give it an initial guess, and your initial guess was 1, okay, and then it outpoints 3.1. But if your initial guess was 2, then maybe it outputs 3.13 or something like that, or whatever, right? Like if you just let it run longer, it might have gotten a little bit closer. But basically, if you were doing backprop, um, you wouldn't necessarily have to backprop through all the steps that the model gave. You might just simply say, well, all I really care about is the last answer was 3.1, and I'm going to compare that to my ground truth label, and I'm going to backprop based on that last little part. Okay, so I think that's a super high level intuition for this. And the whole point of this was to save memory and to save compute. And this is where um, she's saying in this paper, since you ran it for so few iterations, like 2, I don't think you could make the assumption that it has approximately converged to that fixed point. So we're going to do what you asked about, Roger. We're just going to do backprop through time on all of it, um, instead of just doing the last step and assuming that that's a reasonable approximation, that we're already pretty close to our final destination.
Thanks, Ted. I think I followed that now.
Yeah, that's where she's saying that here. While the application of the IFT theorem and one-step gradient approximation to HRM has some basis, since the residuals do generally reduce over time, a fixed point is unlikely to be reached when the theorem is actually applied. So she shows they bypass the IFT and one-step gradient, and so they don't have to deal with it, or don't make that question part of their model. They just go ahead and do all the processing anyways. Um, so she then discusses how they use adaptive computational time, or ACT, um, to optimize the compute on the data sample, and that's shown in this code here. Oh my God, I need more screens. These two functions handle the ACT part of it. And wait a second, I passed. And so then they talk about certain drawback to using ACT. Although the cost is not directly shown in the HRM paper, it is in the code. And the Q-learning objective relies on a halting loss and a continue loss. And the continue loss requires an extra forward pass through HRM. So while ACT optimizes time per sample, it does require 2 additional forward passes per optimization step. Um, so she shows that by with their model, they obviate the need for going the 2 extra forward passes of the ACT. So then she discusses other issues with the HRM based on biological architecture, which is not like the, uh, I guess, current research on artificial networks. So uh, in this paper, they say that that's not really the direction that they want to go in. So they're going to stick with other techniques that are currently used, I guess, in RNNs and others. Um, and so does not try to add the extra steps that are used for uh, to model the biological, um, what we understand to be the biological system. And here's the pseudocode for that she presents um, for the TRM. Um, and as you can see, the code for the deep supervision, slightly smaller, um, uh, although it does some computing through other um, other processing that the HRM version doesn't do, following these functions. But the the part that does the recursive is two-step, where the first iteration is done in here. Well, let's actually go to what they presented. It So in the paper, in this one, she presents that the TRM does not require any more sophisticated understanding of how the model works, incorporating a biological and other um, ideas into the work. Just generalizes the idea of from HRM, and tries to reduce it and simplify it um, to be smaller and possibly less compute intensive and less theoretical, um, and uh, substitutes a single pass for the ACT instead of the two. Um, and yeah, it's presented here in this algorithm, the code here. And because it is simplified, the model can be smaller, and yet yield a better result. So she talks about how, because of the assumptions that the paper that the HRM paper has about how certain aspects from the biological model are going to work, um, because of those assumptions, they code their processes um, specific way to model that and to require certain computations. But here, because they're simplifying the the ideas that they're using, um, they're just depending on I wouldn't say classical, but regular artificial neural network ideas, with fully back propagating um, through the network, and um, with the deep supervision presented here. They take the results from the um, the recursive reasoning um, values, and um, I guess generate the loss functions off of that, from that, to determine where the uh, what corrective action should be taken, and then uses that as input to the next loop. Um, so so instead of gradient approximation, they're just recursively descending through the model. Sorry, recursively descending through the model to yield the results. Is that it?
Alfonso, can I ask a question then on that? So this figure 3, the code that you're looking through. So is the latent recursion, that first function, there's a loop there, I in the range of n. Is that like the number of times the number of recursions that you have in this small model? And then it's wrapped in this other one, deep recursion, which has also got a loop for j in the range of t minus 1. So is it like it's saying, okay, without the gradient, we're gonna run multiple times trying to improve. And then once we have the improved model that's presumably converged because of those T-1 loops, that will then do back propagation through the however many layers you did in the latent recursion.
Yeah, I wish I had a way to show both of these. Hold on, let me try this. Well, no, I'd have to really share the screen. Um, so here, where they're generating the recursive part uh, of the reasoning, um, and all of that is done inside here. Um, they, it looks like an HRM. It splits the computation between these between deep reasoning here, where some of the output extra steps are done here, and the recursion uh, solely within here, within this part, um, or actually it here, no, here they're actually just doing the full processing. It's not recursing any further. Um, I guess all of that's done in here, but if I could, if I cut and paste and put these two next to each other, we could, um, let's take a screenshot.
Yeah, so
Kind of like
while you're doing that, I actually found the HRM paper so confusing, and then I understood it a lot better when I read the explanation of HRM at the beginning of this paper. Um, but when we get into TRM itself, I think she does a good job of naming things in a way that's far more intuitive. Instead of this high, low, whatever business, it's it's our preliminary answer, Y, right? Or Y hat, or whatever you want to call it, right? And so we have our input problem X, we have our preliminary answer Y. And then the one thing that I would improve upon is she talks about this latent Z. I would just refer to that maybe in a more everyday language. Z is your goal. Okay. So the model does a loop and it says, let me refine what is my goal? What problem am I even trying to solve here? And then once it has made its best guess after several iterations of what the goal should be, it then says, well, if that's the goal, how should I change my preliminary answer to this problem? And then it can modify the Y a little bit. And then it repeats both of those several times. And then it says, oh, okay, so now let me rethink some more. Do I have the goal right? Okay, based on my most current answer of what the goal is, let me update my answer. And so you can do that whole business, you know, however many times in your inner repetition. Okay. And so and it's confusing because these are recursive. Okay. So let's say maybe I don't remember what the numbers are, you refine your goal 3 times, you run that layer 3 times in a row, and you update your guess 6 times. You can replace latent recursion and deep recursion with just an 18 layer model if it's 3 and 6. Okay. So you can just say, we did deep supervision on an 18 layer model. In this case, of course, as we talked about at the beginning, you save a bunch of memory by having only actually sort of this one model that you use for all of those 18 different steps. But nevertheless, it is somewhat similar to just using an 18 layer model.
So Ted, am I
Okay, I don't know
following
if
correctly then that the part here in deep recursion with torch.nograd, that's where it's trying to figure out what is the goal. And then when we get down to the line underneath, it's actually doing the latent recursion, which is with gradients. So the model is now learning how to get to that goal in essentially in one pass. In one pass, in this case, you could replace latent recursion with just a model, right?
Yeah, with
It
just in
happens.
this case, I think a 3 layer model that updates your goal.
Right, right.
Yeah. because I think she ended up choosing three. But the code, that's actually not that long, but the code is actually a little bit harder to read just because of the choice of what iterations you do backprop on and what iterations you don't do backprop on. So what you'll see in the deep recursion, so this is the answer recursion. This is the answer repeat refinement loop. It's actually
Mhm.
doing it capital T minus ones without backprop, and then it does it once. So you'll see that there's actually two different calls to latent recursion that are two lines apart.
Yeah, I
Okay.
see that. Yeah.
So it's actually calling latent recursion T times. Only the last one is going to be used in backprop, but it is calling it big T times total. And then latent recursion itself has little n as its loop counter. So I believe they settled on like big T is 6 and little n is 3 for the harder problems like the arc. Um, and so, in essence, the amount of compute you're applying to this is roughly equivalent to an 18 layer transformer model. Sorry, the latent recursor is a 2-layer model. So actually, it's 18 times 2. So it's actually a 36 layer
Okay.
model. One of the things that's confusing is if you look at figure 1 or whatever the diagram, it actually says it's a 4-layer model, and that's a typo. They had experiments where they did 4, but they settled on 2. So, um, but so this is where I was saying in terms of compute, you do you do 6 times 3 times 2 layers, right? 36 layers. And then if you do this deep supervision 16 times, then it's 16 times 36 layers, all told, being computed in order to get an answer.
Okay.
Yeah. I don't know what what my screen is showing right now, so I don't know if you're seeing both code samples
Yes.
or
Yeah,
not.
it's great. We
Okay.
see the screenshot to the right of the actual TRM code on the left.
Okay. So yeah, so yeah, as Ted was saying, I can't highlight it now because then it'll make this code disappear. But um, the the latent recursion is called here through the loop, and then one more time before exiting to, I guess, better close the signal in on where you want to get to on Y and Z. But so what they're doing is so you have in the original HRM paper that had deep supervision because it was going within the uh, over each recurse through the reasoning step, and here they're calling it deep recursion because they're calling it it's being invoked through two steps through the networks to get their results. So it's in this one, I guess they have both deep supervision and deep recursion. But and then again, the illustration for the model, the architecture. And here, Ted was talking about the problem where there was 4 times, but it's actually 2 uh,
Mm.
for each step done through the network. But this is the deep recursion part, and this is the deep supervision. And Z and Y is what they're looking to improve.
Right. So if it helps, the recursion parts have nothing to do with how the model learns. That just has to do with the architecture. That's a choice to reuse layers instead of having individual separate layers. I'm slightly oversimplifying, okay? But if you're struggling trying to follow this, it's best to just think about recursion as how do you build up your calculations just like I said, you could calculate factorials with a for loop, or you could calculate factorials with a bunch of handwritten multiplies. They, in the end, do the same job. It's just how you chose to architect it. Okay. So, so the deep supervision has to do with the training. And to a certain extent, you can say the deep recursion is just if you had 18 layers, how did you decide to sandwich them and build them up into this 18 tall, 18 decker burger, you know?
Let's see. Okay. So what I wanted to see is, okay, so, and
Hey, one question I had, uh, maybe a silly one. Is it deep repetition or is it deep recursion, really?
Go
I
ahead and
think,
use the word repetition. Yeah,
Yeah.
because because
Yeah.
um, I mean, there is one sense where recursion maybe helps you think about what's happening here. Um, but repetition is a very good word so that you don't get super confused.
Yeah. Thanks, man. What really throws me off is what is Q head over there? I understand Z as some kind of latent representation, but what is the Q doing there? And it's also playing a role in early stopping. I just don't get that.
The Q is only there for early stopping. It's completely not necessary for this model. Um, so I'm looking at the time. We're getting a little close to the end, so I'm gonna add a few more extra editorial comments. In my opinion, maze solving and Sudoku are actually relatively easy problems. Okay, they're not trivially easy, but don't forget that this model, when it was trained for maze solving, was trained only to do maze solving. It could do maze solving and nothing else. When you're using GPT-5 or Claude or whatever, you're taking this general purpose model and just saying, here are the rules for Sudoku, see if you can solve this particular problem. Okay. So it's really very, very apples and oranges. If you built a custom network just to solve mazes, I think you and I could build something. It might not be as fast, but we could build something that could just basically do a breadth first search and solve the maze. And so it's not clear to me that HRM or TRM do anything smarter than breadth first search. They probably do, but it's not 100% clear that they do anything better than that. So what happened was when they were training these things, imagine you or I are just training this on like a 5090, okay? Um, they're like, oh, this thing's going to take 5 days to train. But actually, if instead of 16 loops, if it actually has the right answer after only 4 loops, it's got the solution, I could cut my time in 1/4 by just stopping when I already have the solution. And so that's the reason for the queue is it dramatically sped up their training by like 4x because on some of these easy problems, it got the answer long before it did the 16 loops. So it's like a plus in terms of it trained faster, but for me, it's a little bit of a red flag. It goes to show how easy the problems they were solving.
Yeah.
Um, so just to finish up, if you completely got rid of the queue part, it would always run 16 loops and the model would work the same. It would just be slower because it always runs 16 loops.
Yeah. No, it's fine. I think I understand the how Q is used, but I'm just not able to understand how Q is derived. Like, even if I go through the code and the architecture of the model itself, I don't see a place where we are getting Q out.
I
Once
think
we get
there's
Q
just a
out, then it makes sense.
linear layer. It was just a very simple prediction, I think.
Got it. That's okay. We can move on. It's a detail. We can find out. Thank you.
Gotcha, gotcha. Okay, yes. Figure three is pseudocode. They don't actually show you all the code. There's a little bit more code that they haven't shown you. That's why you can't tell where Q
Yeah.
head comes from. I think it's a linear
Yeah.
layer.
Got it. Yeah. Okay.
You can go
So
to the
along with
repo and
the
you can see, but it's very, very simple and fast.
understood. Got it. Got it. Yeah. Thank you, Dave. And there's one other comment that they make in the HRM side 2.5 section saying that the 16 times is run not during train time, but during test time. Did not understand that part because I thought all of this is manipulating laws to adjust the model's behavior, and by that measure, it must all be during train time. So if you look at the very last, they call this ACT, it's only used during training, while the N sub is equal to 16 supervision steps are done at test time to maximize downstream performance. That again threw me off a little bit. Like,
Yeah.
I don't know what they
So
really mean by it.
so again, this was really just because they were training on some easy problems, they would sometimes halt the training early. But when you're going to get scored on the benchmark, you don't want to be 98% sure you have the right answer. You're just going to run all 16 loops. And that's why at test time they did not use their early stop. They could have used
Uh,
it, but then they might have gotten a score that was like,
okay,
95% of their
that
final
test time.
score,
Okay.
and they would have
Yeah,
gotten marks for doing it in a lot less compute. But
yeah,
generally speaking, nobody cares about compute. They're just scoring you on accuracy. So in order to get the max accuracy, they ran it on all 16. And my understanding is some people have posted on Twitter that they modified the code to run it even more than 16. They said, hey, you know what? You get an extra percent of accuracy if you run it on 32. And somebody else said, hey, guess what? I got another 2% by running it 100 times. So it's really just a matter of that compute trade-off thing.
understood. For
But
some,
that's why they always
yeah,
did
I
that.
was confused because I was thinking train test during the model training process, but the test time for benchmarks is an overloading of the word test, I guess.
Yeah. Test time is a right. It's a funny
Yeah,
concept.
yeah.
So
So
then
I'll,
she also discussed,
yeah, I
I'm
was just
sorry,
going to
go
say,
ahead.
no, just going to say, just point out the time and then figure out what do we want to do with remaining time, where you're at. I don't know how far we are, how much longer you expect to go.
Oof, oh my goodness. Yeah, we're about just started scratching the surface of what the TRM uh, theories were and what they were presenting.
Okay.
So if you want to continue it next time or
Well,
another time.
yeah, why don't we keep going till we got another 10 minutes or so here? And then if we want to roll into next week, we can decide to do that.
All right. So they present again one of the drawbacks with the HRM is that they um, they have the two networks that they're using the the low frequency one um, and the high frequency one. Oh, they got a typo here. Um, yeah, so that should be FL. Um, which generates the high level results. And so um, So they in this paper they said that she said that they um, replaced those two networks with one. Um, I guess that's why they do the recursion, or they have a separate loop for running through those results. And she claims by doing that that they were able to get even uh, better results uh, uh, because and less compute because they did need twice the parameters. Um, so and she and as Ted alluded, they had tried the four layer, but found that generalization was worse because of overfitting. So they just dropped it to two, um, while increasing the number of recursions. Um, they were able to get better results in generalization. Um,
If I could jump in on that point, um, I this is some early research. These are sort of proofs of concepts, and so um, I I think the research is very interesting and very innovative. Um, so take this criticism very, very lightly. Um, in the long run, we want models that we can make bigger that will then get better. So we do need to figure out how to prevent overfitting with these models. Again, this is light criticism because this is really good research and it's early, but I consider this to be an almost fatal flaw of TRM as is. It should not get worse when it gets bigger. Uh, it's really failing to, because again, they're running this on toy problems like maze and Sudoku. And I know they got some ARC results. It's not clear to me the ARC results are really generalizable. Um, so in my opinion, it's like you solve some very toy problems. We need ultimately, if this is going to be useful, to find a way where we could build bigger TRMs and have them not just horribly overfit, or it will not be useful. And even then, it's still debatable the whether this formulation can translate to a general purpose model instead of these were trained on just single tasks.
right. So it seems that these models, like I said, because they're so small, they're very special purpose and not applicable to. I mean, they're aiming for generalization here, as she says, but because they're not, uh, I guess, don't handle a larger number of parameters, they're not better for general sorts of problems. They're just tailored to to solve this particular one, kind of like tuning a model for a benchmark as opposed to uh, using the benchmark to test its applicability for certain problems.
Yeah, I mean the analogy I would give is many of us may have done as one of our first neural network problems, solving MNIST with a model with just a single hidden layer. Okay, and you can actually get, I forget, around 80% accuracy or whatever on those 10 different digits. But fundamentally, just a one hidden layer network is not a great architecture for solving hard problems. And if you build bigger and bigger ones on MNIST, it largely just overfits and it doesn't ever get better. Um, and that's a sign that this is not really a great learning architecture in my, In my mind, that's sort of a sign. And so ultimately, we had CNNs that we built, and the CNNs, you could build them bigger, and they didn't just massively overfit when they got bigger. Um, I, I'm maybe doing a little bit loose on my analogy here, but that's where I feel like if the problem is easy enough, like MNIST, and maybe Sudoku's not that easy, but I think of maze solving as being very easy. Um, you might actually just have a fairly simple, not great, not learning, not extensible architecture that can solve it. And it's not necessarily super surprising. That's my concern with this particular finding. It's not doesn't mean for sure that that's the case, but it is a red flag that it could be the case that this is just solving a simple problem with something that's not a general purpose algorithm for building better neural networks.
But is that a statement, Ted, about the architecture, or is it a statement about the training methodology?
It could be some combination of those, and to be honest, it's probably mostly just saying, here's one lone researcher, and she did this, and she did this on one
Yeah,
GPU. We can't expect her to have solved everything. So I'm saying definitely this is not a criticism on this particular paper, but I'm saying on this direction, somebody needs to solve this, or this thing's going to, in my opinion,
yeah,
be a dead end.
yeah, fair enough. Yeah.
Yeah. Um, so she said in the section before, by dropping one of the networks, um, they reduced the number of parameters by half, and and then by reducing the layers, um, because of the overfitting problem, um, they reduced it to two or to half, and again dropped the number of parameters by half. So yeah, it's that seems to be fall in line with that problem Ted just mentioned, where um, if it has a problem with overfitting because of these, it can't use the parameters to uh, solve to be scaled up to solve other problems, then it's very limited and it's used in not the right way to go for the general purpose problem solving. But just in case, she says she uh, references another paper that described optimal performance for two layers in the context of deep equilibrium diffusion models, uh, but and had problems going to trying to make larger networks. Um, so uh, so that may be the drawback to this particular implementation that they have. Uh, that remains to be seen. But when there's not enough data, um, well, yeah, still talking about the overfitting. But here she says it might be that there's too little data within the network. So uh, then you're increasing the memory size of the network in order to carry more um, of the weights and the parameters that you need. Yeah. So this here, using tiny networks with deep recursion and deep supervision appears to allow us to bypass a lot of the overfitting, but that may be a problem with how she's interpreting the results of the experiments as opposed to um, whether uh, Uh, it's a rather than the rather than the algorithm being able to utilize the sparse amount of data that it has to generalize correctly, it may be the problem is that the networks are too small to generalize correctly. So, which direction it is I guess will have to be done more research on that. Um, and she talks then deals with self-attention in the networks, and says that it's proven for long context lengths, um, but for other tasks, a linear layer is cheap, requiring only a matrix of LL parameters. Um, so they replace the self-attention layer with a multi-layer perceptron on the sequence length, and uh, got better results on the Sudoku Extreme. Um, However, we found this architecture to be suboptimal for tasks with larger context length. We show results with and without self-attention for all experiments.
Yeah, and once again, if you don't mind me jumping in, Alfonso, I think this is a huge red flag. If you say, uh, we can just solve this with, you know, a fully connected layer instead of attention, that's a sign that the problem you're solving is very easy in my book.
Yeah, yeah.
Yeah.
But at least they included those the results with the network. But that just may show that other parts of the architecture that they then um, built, that there are other failings or lack of completeness to handle um, the problems that I guess, most people are trying to apply these models for. Uh, it's it tends to be too application specific this way.
Yeah. We're running against our time limit. If I could make one quick comment, um, I've heard people talk about this Sudoku thing. And one of the things you hear people when they're talking about LLMs, and now they're trying to create these thinking models and do reasoning. And one of the things that specifically seems to help is when a model is capable of saying, well, I started down on this track, but let me backtrack and let me try a different approach. Okay. That's a characteristic that people generally look for in some of these thinking traces. And I've heard people talk about how that might be something happening in Sudoku. I don't know where I am on the grand scheme of like skilled Sudoku people, but like at one point I kind of got into it and started doing some really gnarly, crazy hard Sudokus. And for the record, I do no backtracking when I solve a Sudoku. It's completely deterministic. So if you do the bookkeeping, then you say, oh, I see this pattern, therefore this has to be a one. Oh, I see this pattern, therefore in my bookkeeping, I can say this cell cannot be a three. And then it's totally forward. There's no backtracking. And so maybe that's where the fact that the NLP was able to do the Sudoku pretty well, that's consistent with my experience that it does not require complex reasoning. It just requires that you have all the right rules for knowing that if there's already a two in that row, then you cannot have a two here.
So
Okay.
then the back propagation may solve the Sudoku problem as opposed to the deep recursion that there is
Yeah,
used.
yeah. I
Is that
mean, yeah, because some
possibility?
people are saying that Sudoku requires intelligence because you have to say, well, what if I put a one here, then I can't put a two there, then I this, then I that, then I that, and that is not the way that I know advanced Sudoku players solve things. They don't have to do
Right.
any what if. They just simply say bookkeeping, bookkeeping, bookkeeping. Oh, look, this cell cannot be, a 2, 3, 4, 5, 6, 7, 8, or 9. It must be a one. I'm going to fill in the one. And then they're going to see, I see a pattern of these four cells in a rectangle that have these possibilities. Therefore, this one has to be a four. There's no what if involved in the way that I know how people solve Sudoku. So
Yeah.
In
I
other
just wanted to
words,
share that.
yeah. In other words, you could deterministically compute the result of a Sudoku in non-prohibitively large times. You don't need
Yeah,
real
there's no
intelligence.
search. Exactly. We don't need prohibitive times because there's no combinatorial search. It's just bookkeeping,
Exactly.
bookkeeping,
Yeah.
bookkeeping, bookkeeping.
Yeah.
And at
Right.
some
Yeah.
point, you're like, I now know that this cell can be nothing but a one, so I'll fill it in. And
Yeah.
then you keep going.
Yeah.
So
It's
the
not quite
rule
as bad as the traveling salesman problem.
exactly that's what I'm trying
Mm.
to get at is that so for people who don't know advanced Sudoku, you might think that it involves that prohibitive search, but my limited experience with hard Sudoku is that it does not.